Okay, good morning to everyone. I hope you enjoyed the last evening, and we are starting the second day of this conference. And it is my pleasure to introduce our invited speaker, who is Vicent Stora. Uh, Probably a lot of people know this name, at least from reading of the papers, a lot of papers of Vicent Stora. So something about him. He finished PhD study in Universitat Politecnica de Catalunya under the supervision of Claudi Alsina in mathematics and someone who is maybe less known, at least for me, in computer science. And then he uh, went through different working positions as a deputy dean. It was a funny information for me at the beginning of his career through the Spanish Research Council to the Ireland Maynooth University, and in the last years he is in Sweden, first in Skövde University, and now he is a professor of artificial intelligence in Umeå University. He is very active and uh, writing a lot of papers and several books. There are only three of them with Narukava. He wrote a book about modeling decisions, and he is active in the field of data privacy. So he wrote at least two books, at least. And he is a founder and editor of the Transaction on Data Privacy journal, and the key organizer of modeling decision for artificial intelligence conferences from 2004 till these days. Each year conference, the last one was in Umeå, and this year will be in Tokyo. So you are very welcome. His fields of interest include data privacy and clustering and information fusion, and all of that you will hear in his today's talk called Fuzzy Clustering and Fuzzy Measures in Data Privacy. So enjoy the talk.
For your nice introduction. Well, this is the title that Ignacy already presented. So as he said, I'm working on data privacy and besides fuzzy sets and fuzzy measures. And I was asked to give an applied talk. So I will try to link. Well, what I'm going to explain is where we have been using fuzzy sets in data privacy. Most of the things I'm doing in data privacy have not so much connection with fuzzy or fuzzy sets, but we have been using fuzzy sets and particular fuzzy clustering and fuzzy measures in the context of data privacy, and this is what I'm going to explain. Some of you were in Newsflat, and in Newsflat I mentioned some of this. Mainly I talk about fuzzy measures, and at the end of the talk there will be some overlapping with what I was explaining in Newsflat. So, well, I'm here outside the map. This is where Umeå is in the north. This is the Catalan TV map of Europe. So we are outside the map of Europe. So when I was told to come here, well, especially Susanna said that Umeå is not so different because it's cold as here. So to me, the snow is not so big thing. We have a lot of snow, but what I like from here is that we don't have mountains there, and I'm from Barcelona, so I really like this to be here because of the mountains. So this is the line I'm going to give. Well, first of all, of course, thank you to the organizers for inviting me. And besides that, it's the first time I'm in Slovakia, so it's really nice to be here. So about the talk. So first, I'm going to give a brief introduction to data privacy from the point of view of what we are doing, and to give a framework of what I'm going to explain with relation to fuzzy sets, fuzzy clustering, and the use of measures. So this is the first part, and then I will show three different uses of fuzzy-related tools. One is for data protection, the other information loss and disclosure risk. So, well, the concept of data privacy is to use data for machine learning or statistics. So we have data, we want to compute something from the data, and well, of course, data is collected to be used, and otherwise, better not to collect them. And then, well, as you know, you want to build you want models, so when you can make predictions or classification decisions and so on. So the usual approach for this is to build data-driven models. So you have a database, machine learning, you obtain the model, and then you are able to make predictions. So for example, you want to build a predictor from data from a hospital. So you have the historical data from the hospital, and you want to make a prediction about the length of stay of admission. So this data-driven model would be this length of stay admission. You will then give the data of new person that has arrived to the hospital with symptoms or possible illness or whatever, and then the model will give your prediction about the length of stay. So, well, the problem here is that this data is usually sensitive, and well, we need something to protect the
Šárka
data.
Majerová, dobré ráno, neruším. Paní Věro, prosím vás pěkně, chci se jenom...
So here we have the data, and the researcher is the one that wants to compute this machine learning model for this prediction of the length of stay. So this is the kind of the goal. So of course, we can one approach is just to give the data to her, so then she can build the model, and that's it. But of course, this can be problematic because we have sensitive data here, so this is a problem. The other thing is that this person does not access the data directly, but can make a query. Then we just return the query, and then the query would be the same, would be the model of the prediction. In any of these cases, we have problems of confidentiality, because the fact here it's clear that when we give the data, this is problematic. Here it's also problematic because from the model itself, you can learn something. I will focus on the first case. So we have the idea that we want the data directly, because this is, well, most people in machine learning likes to have the data directly to test different models. Then, well, this is not so good, that is better. And for this, we need the data. But the problem of sharing data is that what we call a naive anonymization does not work. The fact that we just take, for instance, a record like this, and then we remove the name, and then we give this information to with all the records, of course, to the researcher, this is not so good, because, well, if you have a town like this, that there is not so much people there, only 600, then probably, even if you remove the name of the person, someone that is there might guess that, well, this record here belongs to this person that she knows, and then it would be clear that, for instance, because probably, of course, the intruder or the attacker knows the town, knows that some person was in the hospital so long, and then we will find the illness of this person. So even if we remove a lot of things, the information, just giving the information is not enough. We need something else. So this naive anonymization is wrong. Well, so what we are going to do? Well, so instead of just giving the data to her, and then we remove, of course, the name of the person. But in addition to that, we do changes into the data. So instead of giving the original data without the name to her directly, what we do is to do something to the data. We do some perturbation to the data, and then we give this to her. So for instance, we can change the age. Here it was 40, here it's 41. Here we change the town, and then we put the district. So we change a little bit of information so that this person here or an intruder in general is not able to find a record in the database. Well, then what happens? Well, of course, if we change the data, there are things to consider. One is how to make this new file in a way that is good. So how to obtain X prime. Then, of course, if we are changing things, just the age of the person, and we just change the town, and we change a lot of things, then some information is lost. So there are things that maybe they are wrong, and then we do an analysis, like, for instance, the mean of the ages, what happens here, that could be absolutely useless. So there is some information that is lost in the process of this transformation. So then we need, so in addition to the method itself, we need some measures for evaluating information loss. This is something that we also need to study. And then there is a third issue that, so we are changing the numbers, but maybe this is not enough for protection. Like maybe we have only one person at age 40, we change this to 41, and the others are 60, and then we have some children of 7 years old. So maybe this change is not enough. So even if we are doing changes, then we might have some risk. We may have some disclosure risk. So a third thing that needs to be studied is the risk of this file. So mainly when we are doing this type of protection by means of perturbation or modification of a file, there are three things to study. One is the protection method itself, then the usefulness of the data after the protection, and then the risk of this data. And for these three aspects, we have been using fuzzy-related concepts. And well, I will explain them a bit. In particular, for the risk, that is at the end of the talk, I will mention record linkage. So the goal will be try to find the person in the database. So it's, okay, we publish something like this. This person knows that Hannah is 40 and lives here. So then the goal is that this person as an intruder is trying to find the record in the database that is similar enough. But this is one of the methods for disclosure risk. There are other things that do not correspond to finding the record itself, but learning something about the person. Okay, so, well, this is a kind of summary of the same thing. So how this is usually done? Okay, so this is done, we have a file X, then we protect the file, we obtain a file X prime. So this is the blue in the previous line, the blue database. So we need a method. Then we need a disclosure risk measure comparing the two files. And then we do some information loss measure doing some analysis of the data. So, well, I have three parts that are these three answers to these questions, and they're answered using fuzzy concepts. So, how can we do the protection? Well, there are lots of alternative methods, and people on data privacy try to just invent methods that are good enough with respect to some metrics. Among all the methods, I will explain microaggregation because this is for not using fuzzy, and then we made a version that is fuzzy of this. And the idea is very simple. So the idea in microaggregation is that we have the database and we make small clusters of the records. Mainly, what we are trying to do is to find groups of people. Let's say if we have a database of data for people, and then we build these small clusters with people. And then when we have this small cluster of people that are similar in a sense, we replace each of this person by the cluster representative. So why this? Well, this is because if we know that each cluster has a number of people, then we have some protection because we are going to have some low disclosure because of this number of records. So if we say, okay, we will build groups of 5 people, well, we have a kind of granularity of people that at the end will be put together, kind of collapsing them into the same person. And at the same time, if we make that the clusters are small, well, then there will be not so big information loss. Of course, if we make just we take the whole population, we do a kind of average, then that will be wrong in the sense of information loss. But if we have a lot of data and clusters are small, then we will have a small information loss. This is a graphical representation of this. So we have here these points, and what we do is group them into groups of at least 3. Then, well, we have, of course, this picture is made on purpose, so we make these 3 clusters. Then we build a cluster representative that we can just use the mean, and then we replace all these points by the cluster center. So we make as many copies as points here. So here, in fact, there are 4 points, here 3 points, here 4 points. And this is the idea behind microaggregation. And well, the formalization is similar to what we have in k-means. So we have well, it's not membership, but crisp. So we have the partition. So this means that we assign, if this is one, J, record J is assigned to the ith cluster, and then we need the cluster centers. So then this is the formalization that is the same as in k-means, but the difference is that here we have that each cluster needs to have between k and 2k. So we are assuming that there is a minimum size and also the maximum size of each cluster. That, of course, the minimum size is to ensure the privacy, and the larger is that we don't have clusters that are so big that we have a lot of information loss. And well, of course, this relates with the C, that is the number of clusters, because otherwise it's impossible. Okay, so this is microaggregation in formal way. What happens is that, well, similar as k-means, this is an NP problem in case that we have more than dimension 2, and then methods are just heuristic. So people define clustering methods that satisfy this constraint, and then they test if the methods are good with respect to risk and utility. Of course, the risk and utility depends on the k. If we have a small k, then we have low privacy and low information loss. When we have large k, high privacy, large information loss. And well, this method, if we take all the methods in the data privacy literature, this is one that is it has a good privacy utility trade-off. And well, you can control this trade-off by means of k. You can, in a sense, play with the k, trying to find something that is good enough for your application or constraints. An inconvenience for this is that it is easy to attack. So if you have some information, you can get the cluster, and this can have further implication with respect to the inference you can make, because, for instance, if you have a class and everybody has the same illness, then you will know the illness of the person. And then I have just used here microaggregation as the whole set. So I have made this cluster in the 2-dimensional space, but you could do microaggregation with different sets of variables, and then you can do what is called an intersection attack, and then you can even find the record. So there are kind of inconvenience. So for this is why I started introducing fuzzy microaggregation, and the idea is quite simple. So in the same way that you have fuzzy c-means and an extension of k-means, you can do kind of the same. So of course the idea is that we can have membership uncertain, and then this as a side effect has that the outliers weight less. So this is good also from a privacy point of view, because the problem in privacy, if you have an outlier, this can affect that result, and then you can learn from the output that this outlier was there. So this has a good effect, and also it provides what we call a transparency-aware protection mechanism. So even if you give the information on how you have protected the data, you cannot kind of reverse engineering in order to go back to the original data. So because you have this thing that you have multiple memberships. In an initial approach, we were trying to keep this constraint on the number of records K, but in a second we just remove that, and then as I will explain here, we use a much simple method just based on C-means, but making a difference. So of course, from the point of view of the fuzziness, we just replace the Chris membership with the fuzzy, as in the fuzzy C-means standard thing. And as you probably know, M here in fuzzy C-means is the degree of fuzziness. So then when M equals 1, you have a Chris solution, and when M is larger, and the larger the M, the more it is, we have that then the solution is fuzzy. And as you probably know also, this is solved using an iterative alternate optimization. So in one you fix the V, so the cluster center, and you compute the membership, and the other you do the other way around. You fix the membership and you compute the V. So we introduce fuzziness in the clusters, and then now I want to distinguish two things, because this will lead to what I'm going to use later, that we kind of decouple the M. What I mean? Well, when we are one thing is when we are computing the solution of fuzzy C-means. So when we are computing the solution of fuzzy C-means, of course, when we have M equals 1, this leads to a Chris solution. So clusters are clearly disjoint. And then when you increase the M, then you have more and more overlapping. And of course, this has an effect on the cluster centroids. So when you have a very large M, you have that all clusters just cover the whole space, and all centers are just in the center of the cloud of points. Well, this is about the computation of the solution. But you can see the solution. Once you have built the solution, you have the centroids and the M. You can see this as a classification problem. So when you see this as a classification problem, so mainly it means that for any X, you can have a membership to any class. Well, of course, this follows from the previous, but it's a big difference, because at this point, we have fixed cluster centers, and they can be in any place of the domain. So you have that M equals 1 means, of course, exactly the same. Any point will be classified to only 1. But when you increase the M and it's very large, you will have that the M is assigned to the point will be assigned to all the clusters with the same membership. And of course, now it's independent of whether you have all the cluster centers in the same point or in other points. So if you have just the points distributed, the cluster centers, this will proceed in the same way. If you have a very large M, you will have equal memberships to all of them. Okay, so what we did was to exploit this fact. And in fact, what we do is to separate the clustering part and the assignment part. So we say this, we decouple M in the clustering and the membership assignment. So we have M1 for computing cluster centers and clusters themselves. So this mainly means if all the centers will just go into the center of the cloud, or they will be just separated. And then we have as M2 that is the membership assignment. And then we just proceed as in fuzzy C-means, but taking into account this. And then when we do, so for microregression, what's important is to build this replacement, because it's the replacement what we are going to give to the researchers. So then we apply the fuzzy C-means, then we recompute the memberships with the second M, and then we assign the points probabilistically with a probability based on the fuzzy C-means probability compute with M2. As you know, this membership adds to 1, so it can be seen as a probability, and then this is trivial. And then after we have assigned the point, we just replace the point by the corresponding cluster center. Well, then we can prove some properties about this based on the M1 and M2. And well, if we can in a way range from zero protection, high utility, maximum utility, to the case that we have total protection and utility is almost lost. And how is done this? Well, it is mainly about how we change the values of M. So if we have that the number of clusters is the same as points, and then we have just that this is Chris, then of course what we have is that we have a cluster for each point, and then we just replace each point by itself. So then this means maximum utility and no protection at all. And then when we increase either M1 or M2 or both, we are having less and less information, and then utility will be lost. But the effects of changing M1 and M2 will be different. When we change M1, we go to the cluster, to the center of the cloud of points. But if we have that what we are changing is M2, what will happen is that we are just changing the probability of going to one cluster to the other. So the effects are different. And in the case of increasing M2, what we have is that if it is large enough, we will ensure what we call probabilistic k-anonymity. K-anonymity is one of the privacy models in data privacy. That means that you have groups of people that are exactly the same. So we can produce this here when M2 is large enough, because we have that the probability will be the same for all clusters. And of course, the size of the clusters also affects the protection. And well, we did some experiments, and with these values, the results were quite good. If we have isolated points, this can cause problems, but we didn't deal with that. But there are, as you know, there are fuzzy cluster methods that are robust to outliers, so that would be something to look to. So then, after this, we did a variation of the same idea, asking for satisfaction of constraints. What does this mean? Well, if you have a data set, of course, you might have relationship between the variables. The variables, in some cases, they are not independent, and then, well, this is a problem, because when you are protecting, if you are introducing noise, what happens is that this relationship between the values might disappear, and this is something that you don't want to. So in some places, like in the statistical offices, usually they collect the data, then they check that the constraints are satisfied. Then they apply protection, and some of the protection methods just destroy the relationship. So then they need to do an additional step in order to correct this thing. So the idea was to do everything at the same time. But there are other methods, as the ones mentioned here, trying to do somehow the same. So the idea is that, well, when we are doing the microregression, we want that this relationship holds. So what it means from the point of view of the optimization problem. So from the point of view of the optimization problem, this means that we need that the solution satisfies the equality constraints. And for us, the equality constraints is just, well, as in the example here, we are assuming linearity in the relationship. So this is one of the variables, this is another one, and this is another one. So we can express them as a linear combination that gives something, okay? And well, here again, M is the degree of fuzziness, and then alpha are the coefficients of the constraint. So we have this here. And well, we formulated this problem, and in the same way as is done with the fuzzy C-means, we solve this by an alternate optimization algorithm and give these two expressions. This is the same as in fuzzy C-means. There is no change, but the computation of the cluster center, this change. So we need to use this expression here. This is the cluster center for the ETH cluster, and this is the component. And we have this part here that this is the different part with respect to fuzzy C-means. And what can be seen from here is, of course, that when the coefficient is 0, so mainly it means that here the corresponding variable is not in the equation, then this expression is just a normal one for the fuzzy C-means. And then the other thing is that we can apply this method with data that satisfy already the constraint or data that does not satisfy the constraint. So even if the data does not satisfy the constraint, the output will be a database that satisfies the constraint. And if not, what happens is that this is just, if it's already satisfied, then this has no effect. And then we can prove some properties for this, and well, are the same, similar to the previous one. So we have that depends on the protection depends on the parameters M1 and M2, and then the larger the M's, the larger the information loss. And we apply the same approach for another type of fuzzy C-means, the entropy base. But the idea is general enough and can be applied to most of the fuzzy clustering methods. So so as I said at the beginning, when we are doing the protection, we have three things to take into account. One is how to protect the data. So this is where we were using the fuzzy clustering. The second one is about the information loss, and the third one is the risk. For information loss, mainly what you need to do is to see how your change on the data change the results. So mainly it's about comparing X and X prime, but not a direct comparison of the data, but on the results of the analysis. So most of the methods for information loss are about computing divergence on functions applied to data. So of course, you could do this with just the mean. So you have the mean of the salaries, and then check if the salaries has changed. Or you can do this with more complex structures. So in particular, you can do this with clustering, then measure the similarity between the clusters using Jaccard index, Rand index, or some of this. So you are computing, you take X, then you do the clustering, then you take the X prime, you do the other clustering, and then you compare the clustering. So we did this with fuzzy clustering, analyzing different masking methods, so some of the methods that exist in the literature of data privacy, and comparing them. And well, the problem with this, or in general with the comparison of clustering, is that most of the methods leads to local optima. So then when you repeat this several times, you get different results, as you know. And this is especially problematic in the case of data privacy, because you take a file, then you do a perturbation, and then you get something, of course, that is different. And then when you compute a cluster here, and you compute clusters here, these are usually different. And then in some cases, you don't know if this is because the data is not similar enough, or it is because you are doing, well, you just go into different local minima. So then, well, we did some comparisons using intuitionistic fuzzy sets in order to have this kind of uncertainty on the clustering process itself, and we were trying to define some measure for this. But the main problem is this fact that different clustering algorithms usually lead to local minima, and then it's very difficult to compare what's going on here with what's going on here. And then in the last part is about the disclosure risk. As I said, there are the three aspects: the protection, the utility, and the risk. So in the risk case, what we are assuming is that we have someone that wants to attack the database once we have protected it. So for this, we can consider what is called the worst case scenario. So we have the data. We change some of the numbers, as I have shown in the previous slides, and then we get something that is different. So then we are assuming someone that wants to attack, mainly wants to find a friend of him in the database. So if we want to assess the risk, well, there are different ways to assess the risk. We can have different assumptions of what this person knows. Because, of course, if this person only knows the town, well, this is the attack, or the rate of successfulness of the attack will be 1. But if he, in addition to the town, knows the age and knows address and knows a lot of information, then it's more, well, the success rate will be higher. So then we have what we know is the maximum knowledge attack, or the worst case scenario, that is try to model the situation that is the better one, the best one for the attacker. And what it means? Well, this maximum knowledge means that this intruder knows as much as possible. So this is the best for him. So it's the best information. Then, in addition to that, the intruder knows how the data has been protected. That, well, this follows what I mentioned at the beginning, that is the transparency principle, that is something that is well known, for instance, in cryptography. So you give the information about the data processing itself, that in this case is also useful, because the data analyst likes to know how the data has been manipulated before getting it. So we might assume that the intruder might have this information. So this is there is the best knowledge possible on the protection process. So he will do kind of transparency attack. And then, well, besides of that, this person can use several algorithms for this process. There are different types of record linkage methods trying to link one file with the other one. So for the best record linkage, one of the ways is to use distance-based record linkage that is based on distance. And then, of course, if we are thinking on a distance, different distance gives different results. So then the distance can be parametric, and then, well, if this is parametric, the best parameters will give to the best result. So this is the worst case scenario. Here, the best information is that the intruders have exactly the same file as here. So he knows as many variables as they are in the protected file, as many records as in the protected file. So knows everything about all the people. And the only goal is to link. So in fact, the intruder will not learn anything else than just linking the record, because he has all the knowledge about, for instance, the town and all the people in the town. Okay, so here in this process of record linkage is where we introduce fuzzy measures and fuzzy integral. So mainly what we did is to introduce them here. So in the papers, most people use for this the Euclidean distance. And then, of course, the Euclidean distance from trying to link records, that is here. So if we have a file and we have a file, if we are doing a distance, what we are trying to find is the distance between the records here that are the original file and here that the ones of the intruder, and here the other ones. And we are using Euclidean distance. This Euclidean distance, of course, means that all the variables here kind of weight the same. So, sorry. So, of course, we can consider other type of distance. We can consider weighted distance. So mainly means that there are attributes that are more weighted than others because they are more discriminative in the attack. Or we can use Mahalanobis distance where we use a covariance matrix because we might assume that there is some structure in the variables, in the data. But we could also use other things. In particular, we could use a Choquet integral where instead of the Euclidean distance, we use something based on the Choquet integral and a fuzzy measure. And we did this. And instead of the Mahalanobis distance, we could use any bilinear form where, well, this Q is in a way learned from the data. So this is what we did. We use these expressions. So we use distance based on this expression, and then we learn this. So that we found the mu that are and the q that are the best possible. So this means that, so if you have no Euclidean distance and then we tune the parameters, we can get more re-identification. So it means that the attack is more successful. So the number of correct re-identification with the weighted Euclidean distance will be always larger than the ones obtained with Euclidean, and the same. The number of re-identifications using the Choquet integral will be always larger than this of the weighted distance, because, of course, as you know, a Choquet integral generalizes a weighted mean, and the weighted mean generalizes the arithmetic mean. So then this means that if you select the parameter right, you cannot get something that is worse. So from the point of view of an intruder, this is fantastic. The better you have the parameters, the better is for the attack. And of course, ourselves as people that wants to protect the data, this gives a better estimation of the risk of this worst case scenario. So that's why we introduced the Choquet integral here, because we have this relationship. And of course, this relationship also happens with the Mahalanobis and the bilinear form. We have something equal, that we have the distance with the Mahalanobis. Well, the bilinear form is always better than just the arithmetic mean. So, well, for this, of course, the problem is how to find the mu and the weights. And then for this, we define an optimization problem. So the idea is based on this graph. We want to link records here to here. So of course, what we want is that we are the people that protect the data and want to have the estimation. So we know which record goes with which record. We know how this should be aligned. So we are able to compute the distance, and we assume a given scenario. So we assume which kind of distance are we going to use, for instance, Choquet integral or just the weighted mean, and then we build an optimization problem using our information about the current alignments. So, and with this optimization problem, we will be able to find the weights of the fuzzy measure. So mainly, what we have is that here we have just a case of the weighted mean because it's simple, but we do the same with the Choquet integral. So mainly we say that we have the records in A and the records in B, and then this represents the distance between record I in A and I in B. And we want that, well, we assume that they are aligned to make things simple for us. So we assume that this goes with the I here, goes with the I here. So then the distance of all the others should be larger than these that are aligned. So, well, then we have that this equality needs to be satisfied. This would be the optimum. Then we can write an optimization problem requiring this. The problem is that this is not in general satisfied because we are protecting, so we are making a kind of a mesh with the file. So it's not always possible to have distance that satisfy this property, that the line ones are smaller. So then we just introduce one slack variable, and then we try to minimize the number of incorrect alignments. So this is what we have here. So mainly what we want to say is, okay, the goal is to have alignment, and this goes with this, and all the other distances are larger. But if not, okay, we minimize the number of cases that this is wrong. And then, well, this is the case of the weighted mean. We can do the same with the Choquet integral. We can do the same for the the bilinear form. And then we just have the data. We put this optimization and compute the solution. And then the solution will satisfy this property here. So we will get more identification than with just arithmetic mean. And with the case of the Choquet integral, we will get more identifications than with the weighted and then the arithmetic mean. So, well, we had some examples in papers about this with the Choquet integral. Here is a representation of the Choquet integral that we get. And, well, this is possible to compute. And we did this, well, for the weighted mean, for the Choquet integral, but we also did this for the OWA and for the bilinear form. This, well, as you know, the Choquet integral has a lot, with the fuzzy measure, has a lot of parameters. So from a point of view of computation, this is complex computationally, and it's very unclear that, well, the gain that you get with respect to the other really is worth the computation that you need to do. But it's possible to compute if the number of attributes is not so big. And well, here, this is just a representation of what I said before. So from the point of view of attack, of course, if you are having the Euclidean distance, this is a very particular case. You will get a number of identifications. But if you have a weighted Euclidean distance or a Choquet, you get more identifications. So from the point of view of attacker, you are you are more successful. So you have this worst case scenario. And the same for the bilinear form. And as you all know, well, what you represent here and you represent here is completely different. So you might have attacks that are successful here, but you are not able to get them with the Choquet integral and in the other way around. And well, with this I finish. So as I said, I wanted to show the use of fuzzy methods within data privacy. So I covered the three things. So on the first part, the microaggregation as a data protection. So it's a way you have the data, you will produce a new file that will be the one that you give to the researcher. Then you can compute some information loss measures using, for instance, fuzzy clustering. And then we use, in fact, this is metric learning using Choquet integral for the case of distance. So that's why it's metric learning for identification and disclosure risk assessment for this worst case scenario. And well, here's some reference. And well, in my book, some of this is explained there. And that's all. Thank you very much.
So thank you very much for your presentation and talk. And we have enough time for a fruitful discussion. So I expect a lot of questions. Okay, so I will start with the one question. When you said something about fuzzy microaggregation with constraints,
Yes.
and can you compare with constraints and without constraints in the case of coefficients or values of M1 and N2? Because for the first case, you said something about close to 1.1 or 1.2. And what is the situation in the case of fuzzy microaggregation with constraints?
I think we use more or less the same parameters, similar parameters. Yeah.
Okay, any question, remark?
Dealing was something with linearity. Have you ever used some other approaches like by Sugeno integral or Schilker?
For the attacks? No.
Yeah.
No, we only use this.
Yeah, okay. It is has its reasons.
Yeah, well, we start because so most people use distance, just Euclidean distance for the attack. In some cases, you change because of course the Euclidean distance, you do the parameter-wise distance, and then you aggregate all this parameter-wise distance with just arithmetic mean. This means the Euclidean distance, of course. So then we wanted something that produce this relationship. We wanted to get at least the same. Of course, we could try the Sugeno, but then we probably would get something different, not fully comparable with this, because you don't get as you know, you don't get the Euclideans as a particular case. But it could be done, but we haven't.
Okay, thank you.
I guess also that maybe this part would not be so simple, but I don't know. Because here with the Choquel, this optimization problem is rather simple, but then this wouldn't be the case for the Sugeno. Maybe some of the results from Belyakov and so maybe would apply here, but I don't know. I haven't thought about it.
Probably better there.
Okay, thank you for the great talk. Two small questions. First, do you need to handle categorical data as well in the data sets? Do you need to handle categorical data set? And if yes, how do you do that? I imagine gender or something.
Yeah,
illness then.
We didn't do that in the experiments, but for this we could just do the same. That wouldn't be a problem here.
In this,
of course, we need to define the distance, pairwise distance. In general, so here we didn't do that.
Yeah.
But we have done a lot of work on attacks, and then we were using also categorical data, and we proceed using variations of distance for that.
Okay, and one more. You mentioned that the representatives of a clusters when then simply replaced. I was wondering if you could also, knowing the statistical properties of a cluster, maybe generate new artificial samples and maybe also generate more than K to make more, confusion. Just a curiosity.
Yes, well, it's tricky this.
Okay.
So in some cases you can generate more, and some people generate more. The thing is that depending on how you generate the more, you don't really protect the data. But on the other hand, there is the positive side that depending on. So mainly this goes to this slide here, no? Here. So of course, you can just do the replacement here, but you can do something else. Instead of just having one point, you can generate multiple points. So this is something that some people have done. For instance, if you do this, the protected file satisfies the mean. The mean of this will be the same as this, but the variance here is lower. So you can generate points here that are not the same, so that the variance here is the same as here. So you can have additional properties.
Okay.
But in some cases, you are giving information that maybe you don't want to give.
Okay. Okay. Thank you.
We still have a time, so if there is another question or remarks or discussion, if not, thank you, Vicens, once more.
Thank you.
that's a little bit longer time for coffee break.